currently working in the assistant professor. He obtained his PhD from NIT, Trichy. Okay, with the MHRD fellowship in the year 2020. His research interests are in the area of control engineering and cyber security. He published various international journals and conferences. He visited the various countries like Australia, Malaysia, Singapore to present the papers, research paper. Next, he is a recipient of Best Paper Award from the prestigious IIT Kharagpur for his contribution towards greenhouse technology, which is the collaborative work with ICAR, NRCB Trichy, and Center for Excellence for Vegetables, Dindigul, the Horticulture Department, Government of Tamil Nadu. This year, she had received IDS Grant Award from ANRF and Best Paper Awards from CES 2024 at VIT and from ETM and 2024 New Delhi. Okay. So she is going to be share his research work as well as the basics of machine learning in the field of smart agriculture, how they are going to be applying the machine learning techniques in the smart agriculture. Okay, she worked in this area. His research area is also in the precision agriculture. Okay, let us hand over the session to ma'am. She is going to deliver the lecture on this topic.
So thank you for the warm introduction and so I know it was a good lunch for you all. To gather the momentum again is little difficult, but let me take up the challenge. Okay, post lunch is always like this. I understand, but let's get back. Thank you for inviting me to be the part of this Atal FPP program. So very interesting. People have coined up the session in such a way that the target audience from various disciplines are able to get something about the topic of discussion. So I appreciate the agenda that you have planned also. So with that, the session 5 is on advanced machine learning applications in precision agriculture. So I'm very glad to be delivering a lecture on it. Okay. So now, okay, a small, maybe this is session 5. You would have got some in details about smart agriculture or smart farming or precision agriculture because it is need of the hour. So let's get back. Okay, I suppose you would have got some insight earlier also because it's session 5. I suppose somebody would have discussed it already priorly, but still, just a brush up for you. So this, what I'm projecting now is the evolution of smart agriculture. So if you see the evolution, when I mean evolution of smart agriculture, it is it is representing the fundamental shift that had happened in the farming methodology. Yes. So if you see the first era, or the, like we are in automation 4.0, we are in energy 4.0 as well. We are in energy agriculture 4.0. Okay, the era is agriculture 4.0 era. So it started with 1.0. What is 1.0? What do you expect? Of course, it is all there in the slide, but still, I want something because it is postal instruction, right? So I want something from you. Okay, somebody can tell what was there in 1.0.
The most natural way.
Natural way, traditional method of farming. There is no tractor, nothing. You have only a family practices there, some traditional method to plow the land. Yes, you do it in a traditional way. So that was the initial. You see there, it was family oriented job. Okay, you have a small piece of land. I plow my land, I sow it, I reap it, I do everything in a nutshell. Okay, it is now the entire family is into agriculture, maybe. So that is the first era, wherein there is no mechanized automation, anything was not there. You have traditional practices to do. So that comes under exactly very true. The first era is use of humans and animals. Yes, you had bullocks, you had the animals deployed for job in lands. All that were the initial practices that we had followed. Yes, the way, what the generations have passed, that I will follow and do agriculture. So that is era 1.0. So what you see is agriculture 1.0, it started. No, I cannot define it. It is, okay, this is from, I have to give a proper citation, but due to like urgent, I just skipped even the citation. So it is 1.4, somewhere 1780s it is mentioned, which was defined as, okay, we can frame it as era, but earlier days, the farming started very earlier, much earlier. But the name we coined, okay, we should separate into era, came into mind only in 1780s. So you had basic use of animals and humans, okay. So we started from nothing, okay, to some new, few tools were used, okay, man-made tools were used. Properly we know what is agricultural practice. So that is 1.0. Next is agriculture 2.0. So it is, in the year they noted to be 1950. So what is that great with this era? Anybody? What is so great with this era? Yes, somebody. After independence, okay. This is not only with Indian scenario, okay. We are talking in a greater context. Revolution, green revolution was it was in this period, green revolution started. So what was the major part of green revolution? You had mechanized tools, mechanized instrument was used, tractor was used, yes. You had use of chemicals, okay. And if you see, they had an exponential turnover in terms of yield. Okay, the agricultural yield or the produce was exponential. So then it was called to be green revolution, because by traditional methods of farming, they were able to achieve some yield. But with green revolution, the methods of agricultural practice has shifted. You have moved to mechanized equipments to be placed in agricultural practice. So all this paved way to increase their yield. Okay, the labor job or the tremendous labor-oriented job were cut off. Okay, here instead of animals and man's burning themselves in the land, so they now had some mechanized vehicles. Okay, to do the same job or serve the same purpose in the lands. So this was called to be the green revolution era. So that is the second period where mechanization. So we have the years from 1900 to 1960s dedicated for era 2.0 or agriculture 2.0. So you had introduction of tractors, basic machineries were there, and then improved efficiency, because now the labor is cut down in certain terms. Okay. The next era, agriculture 3.0. So 3.0 is use of high-speed automation. So what the topic? Precision agriculture. All that precision. Okay. You don't simply sow in your land, but you precisely sow it. You don't simply irrigate, but you precisely irrigate your land. Everything done with precision. So this era is termed to be precision agriculture era. Okay? All you do in terms of precision. Okay? So now it is use of high-speed automation was there. Yes, I suppose in the earlier lecture, Anish would have discussed about some IoT these are. So that all came as a part of agriculture 4.0, and we are working forward. Okay? Because why we should work forward? Why should we deploy all? Why there is an evolution in the era? Okay.
We need to obtain a good yield.
Yield, yes, of course. Now, the land that is utilized for agriculture is cut down. Yes, the land that is underutilization for agricultural purpose has cut down. But we are no longer, our population has not cut down at any point of time. We are growing, but the land utilization for agriculture has not seen that growth. So you have certain resource, limited resource within which now you are supposed to take up agriculture and meet the demands, okay, the growing demands. So that is in picture. So the agriculture 3.0, which is supposed to be the precision agriculture, and agriculture 4.0, which is integrating the IoT devices. So it was, when I call precision agriculture in 3.0, it is then when GPS technology was introduced, okay? So precision in what terms? Centimeter level precision I can achieve. Yes, I can sow where I want to sow, okay? Seeds are sown where I have to sow. Not in all just barely throw the seeds over the field. It is not so, okay? So GPS operated tractors are in practice, okay? Which means in the given longitude and latitude, I will check for if there is a pest. If there is a pest, I will inject pesticide, okay? I cannot simply use to destroy weeds. I will not simply apply pesticides all over the land like that, but instead precisely go there, inject it over there, particular GPS location where it has identified weeds. So that level of precision level is centimeters level. So that level of precision is being achieved. So that is with agriculture 3.0. So you have GPS technology, variable rate application. So variable rate application is that in a large field, it is not irrigating all the area with uniform water, okay? So the irrigation is dependent on where there is a need, where there is a drought, where there is a stress. So there I inject more, or I irrigate more. So you have variable rate of use of fertilizer or variable use of irrigation, all are brought into picture, okay? So that is with respect to agriculture 3.0. You have basic sensing technologies. So basic sensing technologies, yes, I insert a sensor. I'll understand what is the soil nature, what is the climatic condition. Just an open field, right? Everything I'm trying to measure and appropriately take some action. Yes? So that is with respect to agricultural 3.2. So next is agricultural 4.0. With this, you have what was your last session all about? Integration of IoT, yes. So now you are trying to communicate the data in real time, okay? What is the current temperature? What is the current humidity level? So you are not measuring, you are not going and noting at each point of the field, but rather you are remotely monitoring. You are sitting somewhere, okay? You are trying to remotely monitor the real-time data, okay? What is the current temperature? What is the current soil moisture content? Everything you are trying to monitor in real time, okay? So that is possible with use of IoT and AI and robotics, yes? So beyond that, okay, now even IoT is not in picture. More than beyond IoT, what happens is that you have something called as edge computing. Edge computing is nothing but the sensor itself can take its own decision based on the measurements. So no, data is not sent to the cloud, it is not remotely monitored, and action is not taken appropriately. So there is a time, okay, there is a time between the point of measurement and the response control action to take over. So instead, the edge computing or edge device technology is that the sensor itself takes the measurements, the sensor itself will know what is the decision that has to be made in the sensor level itself. So it is called to be the edge computing. So the next level, we are moving into the way forward. Yes, IoT, we are extending it further with edge computing, edge computation. So all done at the edge level, node level itself, okay? There is no transfer of data remotely. So this is what is project line of how our agriculture practice or the in some agriculture 3.0 or 4.0, whatsoever. We are there in somewhere like there. Now, why there is need of ML in this modern farming? I have not written anything because I want it from you.
Because we want precise value in each parameter.
Yes, why ML is required? ML, machine learning is required. Why there is an intelligence required now? Tell me.
Because through that only we can communicate.
Communication is IoT. Why machine learning algorithm is required? Predict, okay, decision making, all are good.
To minimize human dependency.
In what terms? Almost in agriculture 3.0 we have cut down the labor.
Fully automation.
Fully automation, only automation. Machine learning is there in automation? No. There is no machine learning in automation. There is no intelligence in automation.
So decision will take automatically without human intervention.
Okay, accepted. But why there is a prime need of ML? So what happens is that when you go into agriculture 3.0 or 4.0, what you have? You have data coming out from the sensors. All from the sensors, it is expected that we have terabytes of data annually recorded from a farm. Yes? So you sit and analyze all this data. You cannot sit and do. You cannot analyze. It is not an Excel going to do this job. Okay, so many. Your soil only can measure, a single soil sensor can measure up to 12 parameters related to soil. Yes? So if it is going to give hourly data, you think of the data that is emerging out annually. It is terabytes of data. So in order to predict the yield, or if you want to handle the data, a man cannot sit and do it. Yes, there is an intervention of intelligence required from computer algorithms, okay, to understand what is the data all about. Okay, I am trying to shift my intelligence. What do I have? I am just transforming the intelligence what I have obtained through generations and just transforming through algorithms. So that is simple as machine learning is. Okay, there is huge data. They call it to be the data explosion. So that explosion is there. Who is going to handle all those data? Right? So in that case, what happens? You need some algorithms. Instead of it has to, all the human interpretations or decisions has to be automated. Okay? So in this case, you need some algorithms to come in picture, evaluate the data, analyze it. What is the decision that I have to make? So a person or a farmer who has experienced to take up a decision is now my algorithm is going to take. Yes? Appropriate? Yes, because there's a lot of data coming up. So now, all thing one has to do is, with respect to, if you have shifted your methodology or practice from agriculture 3.0 or 4.0, now you have to learn machine learning algorithms. It is mandatory. It is part and parcel of the era. So one has to understand the password, it's locked.
1, 2, 3, 4.
No, sir.
Just a minute.
So this is a prime reason why one should go with machine learning algorithms. Yes, this is the very prime reason. I have data. I cannot again deploy a person to evaluate the data. So you need some algorithms. Okay. I suppose you are from multiple domains. We have somebody from computer science also. So you will be able to now appreciate machine learning algorithm, how it is being deployed in the stream of agriculture. Okay? So it is not only the software technologies used, else applications, it is majorly used in farming level also. Okay. So now, this is the reason we should need machine learning algorithm in agriculture. So apart from it, so what are the key drivers? So now, when I talk about the key drivers for this modern farming, so these are the reasons that we are going, or the key drivers for the modern farming that we have adopted. The first one is the population growth. As I told you, the population growth is exceeding, okay, it is exponential, but the land utilized for agriculture is not growing as equal to our population. One has to understand that. So we have all limited resources. 2050. This is the statistics. We have to increase the food production by 70%. Is it feasible? Yes, it is. It has to be done. Otherwise, we'll die out of poverty. What poverty? Food poverty. Yes. So this is the essential need or the key drivers for modern farming. The next thing is that climate change impact. So we have very unpredictable weather. Yes. Somewhere now we expect to be winter, and some areas it is heavily pouring. Yes. So we are not. Our delta farmers are struggling very badly for the past cyclone. Okay. So our weather is totally unpredictable. So now we have jumped in a scenario where the global is seeing a shift in climate change also. That is one driving factor why you should go for modern farming. So at end of the lecture, I will be discussing a paper which is on greenhouse technology, the work. So where you don't have open field farming, where you have an alternative method, that is controlled farming, which is the greenhouse method of cultivation. So I'll touch it upon in the last point. So next is resource optimization. So not only in terms of land, okay. Now not only open field farming, we have gone into vertical farming. All methods of farming we have introduced, but we are trying to optimize the resource. Not only land is a big problem, but even water. Okay. So sometimes our Tamil Nadu itself faces a bad drought, and sometimes it is flooding like this heavily. So it is unpredictable, and we are in urge of cost optimization also. We are much concerned about cost optimization. So for this all reason, I put it in a holistic way. You should go for resource optimization, be it water, land, or the cost. You have to optimize it, or else nobody is interested. Okay. So these are the things that we are projecting in the modern farming. So now, labor challenge is the greatest challenge that the farming sector is facing. Okay, there is no person ready to go or get into the farm and show themselves as a farmer. Okay, nobody is now the trend has shifted. Yes, we are all moved to white collar jobs and all, and there is a less interest towards the farming practice. So that is a major challenge that agriculture field is facing at now. So aging farming population is the population who are involved in agriculture have come down, and you have labor shortages. There is nobody. You have it is about to reap. Okay, but you don't people to work in the field at the time to reap your yield. There's nobody is there. The labor shortage is there. Though they have mechanized vehicles, to certain farmers it is little. It is not favorable because of the affordable costness. So that are the reasons for or the key drivers where your modern farming is facing. So now I can bring it in those terms like in terms of production, the production challenges that has been faced recently. So I have so much problems, okay, when it comes to agriculture. Though I move into era 4.0 or 5.0 whatsoever, I face a lot of challenges, okay. So challenges in terms of primarily resource management. Okay, what other problems do I have? Water use efficiency is one big problem that is lying in front, okay. Every state needs water, okay. But then the first point that I have to talk about resource management in terms of agriculture is water usage efficiency. They call it to be WF. So how much water is being deployed for agricultural practice of unit area. So that is calculated annually. So that is, they call it to be the water usage efficiency. How efficiently you utilize the water in bringing up the yield. So that is the terms of efficiency they talk about. So that is the first prime thing. Next is soil health maintenance, and you have nutrition management and energy consumption. So energy consumption is also playing a part, okay, added at the last point. But majorly we are bothered about water use efficiency, the soil health, and the nutrition management. So in terms of crop management, yes, there are again kind of challenges that the agricultural field, the farmers face in terms of crop management. First is disease detection, then you have pest control, yield optimization, then you have quality control. So these comes under the category of challenges across crop management. The challenges that you face in terms of environment factors is that you have climate variability. Okay, so climate variable is a big concern. As I told you, this is a big concern which is unpredictable. Next, you have events that are we even right now we face our fields getting demolished or destroyed due to extreme events. Okay, so recent cyclone is a better example for it. So it is not predicted one. Of course, if you predict also, you cannot predict so early so that you take some measurable actions. But it is only predicted before a week or 10 days before, but the sowing period would have been long and over. So in those terms, the extreme events play a big picture in determining the yield condition or the produce. The next is soil degradation because of utilizing multiple fertilizer and all that. Your soil quality deteriorates. All these are the factors that are faced. So the operational review, as I discussed earlier, it is the labor availability, equipment efficiency. I have an equipment, I would have a better alternative also, a modernized one. But due to affordable nature, I will be opting the other, which is of less affordable, which of less efficiency. So we have the factor of equipment efficiency, we have cost management and market volatility. So these are the challenges that are just staying in front, okay, with respect to our era of farming. So now we have some sophisticated solutions, okay. When there is a problem, there are some sophisticated solutions also coming up. So why I call it to be sophisticated solutions? Because I have some technology involved to solve some certain aspect to an extent. I cannot simply tell my solution, technological solutions can be a remedy for extreme weather condition. No, I can predict only to an extent, okay? Not at the point of sowing, I will not know after 3 months there will be a cyclone. No, that cannot happen. Okay, so there is a limitation with respect to technology perspective as well. So now we have one solution is like data-driven agriculture, a new paradigm which is emerging as one of the solutions towards this modern farming or modern agriculture. So okay, so now data-driven. So when I call it to be data-driven, so data is available to take up some solution or measurable action. Okay, the first point is data source, then I have to talk about. So when I talk in the context of agriculture, the first data source is the field sensors. So I've listed, but be it an open field or be it a controlled environment, so these are mandatory sensors, field sensors. So field sensors to understand the condition of the soil, okay? Soil moisture, temperature, humidity, nutrients level. So these are the basic sensors that they deployed in the field. Hence they are called to be the field sensors. Okay. The next is we have gone into sophistications. So now I have imaging systems. Okay. Our first one is satellite images. When first one I have just listed is satellite. So you have Landsat sending every 5 days a data which is of resolution of 10 meters. 10 meters resolution, it is going to send a data, satellite communication. So satellite images, I get it every 5 days. So that resolution is 10 meters, okay? Somewhere from the satellite, it is capturing your area with 10 meters resolution. That is the advancement in technology. Yes? So you can understand the field pattern and everything. So when you have an epidemic attack, okay, you can understand where it has attacked. What is the nature of the attack over a period, all from the satellite images, okay? So you have satellite imagery.
Satellite image is costly, so we can't able to.
No, actually there are set of, you cannot take it in the sense, if you are interested, there is a data set available, okay? So the data set is kept as open, not for your particular field. That is I'm just telling about the technology advancement.
And temporal data for every 5 days it is not available.
Every 5 days it is because that is the open access maybe it not be available, but the Landsat sends the data every 5 days. So if you measure some epidemic disease, then government or somebody who is interested in analyzing will go for data analysis. So that sophisticated solution is available. Not so that is what we cannot afford all technologies. Okay, at our level, still farmers cannot afford all the technologies. Farmer will not a farmer who's there in Chidambaram. Okay, we expect them to adopt to the newer technologies. Okay, though it is not affordable, we see that in due nature or in due time, it is going to come down. The cost would come down, and everybody is able to access the technology solutions. So this is one of the technologies. At any point of time, the person of interest who is under research or the government organization who are into this research will take up or utilize the data. Okay, so that is what. So imaging systems are there. So at field level, what I can do, I can fly a drone. Okay, I can fly a drone. Okay, again this is not affordable, but still I have an immediate solution. Okay, I can fly a drone, capture the image. Okay, in multispectral data I will be able to analyze. So that is possible. So under imaging you have drone technology, multispectral imaging, LiDAR data, all are possible. These are the feasible solutions. I'm just projecting you all the solutions. So now equipment data. So you have machinery performance. So we talk about energy efficiency all. So now I have to measure it. So equipment data is also mandatory because it is projected in our challenges. So there you have machine performance, operational metrics. Even people are ready to talk about ergonomics. Okay, ergonomics data of the farmers who are involved in farming practice. So so you take up all the data set is available. So now where do you use it? So when I asked why ML is why you need ML, people were among this crowd, you people were able to identify few applications. The same I have listed also. So one application is yield forecasting, weather prediction, disease outbreak prevention. Okay, and you have resource requirement planning. So under these categories, we'll have our data applications. So you have data. Now I apply this data for all these purposes. Okay. Today I will discuss three among them. Okay, in detail with respect to machine learning aspect. Okay. So quickly, this is integration of ML and smart farming. So you have under three categories. One is crop management, resource optimization, and decision support. So there you have lot of sub applications. Okay, these are majorly they are grouped under these three categories. So now when it comes to crop management, I can have the application of yield prediction, disease detection, growth monitoring, harvest timing. So now I'll be able to plan my schedule based on the weather predictions. So that is possible. So that is crop management. Okay. Now for the next few months it is going to be drought. So let me not plan anything. I just simply prepare my soil for the next drought. Okay. There are some provisions for you to plan. You predict something and you plan accordingly. So that is provision is there with respect to the smart farming methods. So next is resource optimization. You have irrigation techniques, which is irrigation scheduling. Okay. So one of the applications which I cover is irrigation, smart irrigation. I just let you know during that time. Next is fertilizer application, pest control, and energy management. So these are the categories of applications that come under resource optimization. Next is decision support. So when I talk about decision support, it is major because you are talking about risk assessment, market analysis, operation planning, and resource allocation. So decision support, it is going to ML is going to act in a greater way in decision support. Okay. So now I told you like we'll be discussing about three applications along with ML techniques. Okay. So first line I mentioned, significance of ML in agriculture is beyond automation. So is that the case that when somebody told automation, I told automation does not require machine learning. Okay, you set some code, okay, some logic, okay, you set a duty cycle for sprinkling, it will just sprinkle as it is. So there is no intelligence there. You command it, it does it. So it is automation. Okay, but intelligence is different, or machine learning deployment in agriculture or any walks of engineering or any walks of science is different. Because now it is beyond automation. When it has to spray, okay, when it has to irrigate. So all that matters. So significance of ML in agriculture extends beyond mere automation. That is the first point to note. Next, it addresses the critical challenge of global food security because it is need of the hour. As I told you, this 70% increase in agricultural practice has to be there in order to meet the global needs. So that is one prime thing. So we are all we are very much worried about future. Okay, when it comes with respect to global food security. So that is one important thing. So we have to have certain reserve conservations and sustainable farming practices to be picked up by all. So if everybody is able to go about resource allocation and sustainable farming practices, if they are adopted only, then we'll be able to have some increase. Okay, a threshold increase at least in the yield or the the produce, agricultural produce. So the modern agriculture system generates massive amounts of data from multiple sensors, including satellite imagery, IoT sensors, and the field equipments. So the ML provides you a tool to process this data, extract something out of this data, okay, and take some decisions that is applicable to farm management. Okay, so that is the prime motor. So today I will be discussing, or what I would cover is yield prediction, disease detection, and resource optimization. So I'll be able to cover, I suppose I'll do it. So this is what we'll cover today, and how ML is integrated in all these applications we'll understand. And why I'm just trying to cover this, because yield prediction is directly impacting the productivity levels, productivity. And if I talk about disease detection, so if I'm able to detect a disease at an early stage, I would be able to take appropriate decisions so that your produce or the yield is not greatly reduced. Okay? So timely or early detection in terms of disease is essential. Okay? That facilitates or enhances the decision support. The next thing is that resource optimization. Of course, it is need of the hour because we are doing farming with limited resources. So efficiency in resource with respect to resource is also important. So now, okay, anything for that matter. So first I will be dealing with ML-based yield prediction. ML-based yield prediction, which will be my first topic of discussion. Next I'll deal with disease detection. Next with resource optimization. Okay. So ML-based yield prediction systems. So you have data coming out from multiple sources, right? You have installed field sensors. You are taking images over the field. Yes, you have equipment data. So many data are there. Terabytes of data are there. So in case now there is no worry about data sources. All data are available. Now how this data is going to help me with yield prediction? That is what is the topic of discussion as of now. So now you have field sensors and remote sensing based data sets. So when I talk about remote sensing data sets, so they will provide me or they will facilitate me to take up the index which is called to be the normalized difference vegetation index, and you have EVI, which is enhanced vegetation index. So these indexes are going to give me the insights about the crop health and their development. Okay, how is the crop doing now for this season, for this period of for this cycle? How is the crop health? Okay, at present what is the crop health? What is its development stage? So all that I'll be able to assess through this index. So I'll be able to get all these details from remote sensing database. The next is field sensors. So as I told you, your temperature, humidity, soil content, nutrition content, measurement all goes with this field sensors. From this you will be able to get the ground truth reality. Yes, you know what is exactly the temperature now. You know what is exactly the humidity level now. You know what is the quality of the soil or soil health now. So at present you will be able to give the ground truth reality. Okay. So field sensors contribute to the ground truth data about the soil conditions, microclimate. So when I talk about microclimate, it is temperature, humidity, moisture, everything comes in packet. Okay, and crop status. So sometimes you refer to history of data. Okay, some historical data is also important because it is going prediction. So history yield data provides you the foundation for training the prediction models. So this is the basic data sources and what you are supposed to do with this data. Next is, okay, I have data. I told you that this data is used for yield prediction. Okay, the first case is yield prediction. Now how this is going to work, how your ML models are going to work with, get aligned or integrated to your data. That we'll understand. Okay, so first I do some feature engineering. I call it to be feature engineering. I have some data. Now I just take out the features from it. Okay, I just first classify whether it is a temporal data or time-based data. Temporal data, I take the spatial features and I just understand what is the weather pattern. So this is first thing I do. If I take up a data, I clean the data, all processing is done, the basic processing. Now we have edge devices which does the pre-processing in the edge level itself. So there are sensors to do the purpose of data cleaning and all that. So the next thing after you get the data is feature engineering. Okay, you segregate, you extract the features, you segregate them. Whether it is temporal, it is belonging to the temporal data set, or spatial feature is it, or whether it is an environment related data. You just segregate them. Next you do, okay. So now here is the real picture. Machine learning. Because I have the data, just simply classified or just gather them across these domains. Now the next thing I do is, I have to analyze the data. So next thing I do is that, give this data to the algorithm, okay. So now my algorithm has to give me or predict what is the point of the discussion now. What the data is used for? Yield prediction. Okay, now my model has to work on yield prediction. What is the output? After 6 months or after 3 months, what you are trying to predict your yield. This is the soil condition, this is the nature of the season, this is the rainfall that would be received. Upon this, I am just trying to predict it. Okay. The first methodology I use or people prefer is random forest approach. This is one machine learning technique. So as of now, you just understand the name. If you are not from the background, you just get to know what is the words only. So random forest, you have long, short term memory, that is LSTM networks. Next you have CNN for imaging. So these are techniques across where you apply the data, and these algorithms are going to help us in analyzing something. Okay? So that is the thing. So now so in order to implement this, you should have you should follow the model pipeline. So you have to pre-process the data, and you have training process and validation process. So data set is available. I convert or I choose 70% of the data or 80% of the data for training purpose. Okay. So training in the sense, now my algorithm is very raw. I have to teach my algorithm. Yes, I have to train my algorithm. So all that I set or select certain percentage of the data and utilize for training process. Next I have certain set of data being saved or secured for validation purpose. So this is the model pipeline I do. First data pre-processing, and then I have some set of data that is available for training and validation. Okay, now I have applied. Okay, you imagine that I have done all these model pipeline process I have done. Now what is that I get? I get some yield to be predicted. Now we have not understood the methodology. Okay, we will try to understand in the next slides. Now my algorithm has worked out on it. Okay, there are various algorithms. So these algorithms have worked on the data set that I have given. Now it is going to give me predictions. Predictions on yield. What should be my yield? So it is going to give us. So now to validate my predictions, I go for performance measures. Performance metrics I use to evaluate my machine learning model, which I have trained. So that is analyzed or evaluated across accuracy ranges, error measures, and some validation results. Okay, I have done validation process also. Some validation results I will have. So I am just trying to understand the performance of the model that I have trained. Okay, just barely some algorithm is doing some purpose. The purpose to be here for this estimating what is the yield by taking the data set. So now we'll understand all this, okay? We'll try to understand. So random forest, which I have mentioned first, is excelling handling data which is of complex integration. So when there is multivariable, they call it to be multivariable integrations. So where you have multiple factors that are going to affect a parameter, okay? So that is complex integrations between multiple variables that is going to affect your yield. So that is going to that can be handled well by your random forest algorithm. So there is people who have worked tremendously on random forest and they have understood, okay, or your literature says that your random forest algorithm can excel where or it can handle complex interaction between your multiple variables that are affecting your yield. So this is one inference, okay, this is one they call it to be inference drawings, okay, from various people who are worked across, they are trying to draw some inference. So this is the first inference. Next is LSTM works or the LSTM networks add capability to the model temporal patterns. So when you're working on time-based patterns or temporal patterns or seasonal patterns, then your LSTM is going to work. Okay? So particularly it is important when you're trying to capture weather effect and the crop development stage. Okay? If you're supposed to understand the crop growth, if you're into crop growth analysis, then or what is your weather prediction, what is your ambient weather that you have to predict, then your LSTM will work. So I just given here out of literature survey. Okay, so this is majorly your LSTM is used for crop growth analysis. And the next is CNN is which is going to work on the spatial data. Okay, basically CNN works well with images. So one has to understand your CNN works with image data sets. So here in agriculture or here in this context, CNN process spatial data from the satellites. So from the drone imagery, extracting their features and understanding the crop health or crop conditions or what is the field variability. When you are talking about the satellite images, you will be able to understand the field variability. So if you are taking up with a drone or very localized images, then you will be able to understand what is the crop condition. So you are trying to work on images that are captured at using various sources, and CNN is going to help you with those images. So this is all I have just marked over here. This is out of the literature survey. So the first case study, so I have a field over there. I just have the crop area and production data all set ready. So I have some environmental data as well. I have it them as raw. Then, so now whatever this is data set, so I have selected some 5 regular crops for that matter, okay, and crop-wise data set is being developed, okay, crop-wise data set. So you have data for potato, wheat, so crop-wise data set is collected, and you first going into the process of data cleaning. So before that, when you are trying to capture the data, if you're working on soil data, you should capture every 30 minutes. Okay, if you're working on weather data, then you have to capture or record your data every 15 minutes. So if you're working on satellite imagery, you can have weekly data. If you're working on drone imagery, you can have bi-weekly because you're trying to understand the field nature, that's all, the images. So this is the sampling rate for that matter, that you capture the data. So now you have some data available. The first thing I do is pre-process the data, otherwise called to be the data cleaning methods. So I apply data cleaning methods. So what is data cleaning? So I take at the samples, right? 30 minutes, 15 minutes, I take some data. Sometimes if my sensor is not sending some data, okay, consecutively twice it is not sending. So some data is missed, okay, then I can able to fill those data. Okay, just analyzing the nature of data that is being received, I can able to fill the missing data. Okay, which is sometimes it may send inappropriate data also. Some junk message would come from the data. So that all I just mitigated using the first process, which is called the data cleaning. So I can handle missing data, wrong format, wrong data solutions. All that is it is rectified at this first stage. So first is identify the methodology for data cleaning. Next I do is pre-processing. So data integration, data transformation, and data reduction. So I now have data is coming at different sampling rate, okay? First thing I will have to do is first normalize them all, okay? Normalize for with the zero mean, which means my range will be from -1 to 1 or from 0 to 1. I normalize it, okay? Convert, if I, what is the expected range for temperature? If I am getting a temperature data, what's an expected range? In a typical temperature sensor, they will be giving you a range. What is the range? Approximately.
120 room temperature.
Range? No, I'm not asking what is the temperature of the field right now. What is the range that the sensor will? There will be a data sheet coming along with the sensor. So they will be mentioning what is the range.
0 to 5 sensitivity like that.
Sensitivity will be there, but the range will not be mentioned. You cannot deploy it in a boiler. No, range would be mentioned. So for an ambient temperature sensor that is deployed in agriculture, what is the range?
So according to application, it's getting varied, ma'am. We cannot say.
Application is agriculture application. Open field agriculture application. We are in this context, right? 40. Your temperature does not go beyond 40. Go to Rajasthan, it is more than 40. Huh? At least you will have a temperature range till 60. Okay, 65 at least. Okay, so this will be the range. So now for this range, if my temperature at present is 30, okay, say my range is this. Now my normalized value would be, if the range is 0 to 60, my temperature value right now is 30. What is the normalized value? 0.5. I'm just scaling the range from 0 to 60 to a scale of 0 to 1. That's all. So because why do I do this? Everybody or all the sensor work on different ranges. Okay, your humidity sensor work from 0 to 100%. Relative humidity. Okay, so I cannot simply use this data. I normalize the data across the scale 0 to 1 or sometimes 0 mean, which is -1 to 1 for certain applications. So we generally do 0 to 1 normalization. So when you are doing it in some research work, you don't take the data as it is, you don't record it. No, you have to normalize before using it in the machine learning algorithms. Okay, the first process that you do is normalize it. So now you integrate the data. Now you have a data with different varying sampling rate. Now you timestamp it. Okay, that is your data integration. At this particular time, what is your temperature? At this particular time, what is your soil health? Okay, what is your nutrients level? So you timestamp it. Okay. So now you will be able to integrate your data. Now you go for data reduction. Sometimes when you want to scale up because you don't want every 15 minutes data, so you pick up what is the sampling time. So you accordingly go for data reduction. Now you go for ML. So as of now, we have not opened the book of ML at all. Some algorithm is sitting inside this basket. Okay, now data is clean, everything is ready. We are applying this data and coming out is some prediction rate, prediction of yield. Just assume. It is still now a black box only. We have not discussed anything with regarding to ML. So there is something sitting again here. So it can be an SPM. This can be a rainforest algorithm. It can be an KNN. Any algorithm for that matter. So there is some algorithm sitting inside, working, taking all the data inputs and giving me the output as yield. What is the output? Okay. And now I check along the values that I get. I check it along the validation data. Yes, if it is appropriate, I measure across your performance metrics, which is your mean square error, root mean square error, you would have come across. So all these performance metrics are there to evaluate your machine learning algorithm only. Okay. So now it is there. Okay. Now, okay, this is again from literature. So people from a systematic literature. So you have people will take all these data sources to understand the crop yield. So what I have it in blue, marked in blue are concrete data, okay, which are mandatory required for yield prediction. Okay, so I should have data about the crop information because it may be a wheat, maize, the basic information of the crop is important. So crop information, then you should have the soil information, the humidity levels, the nutrients, the field management and solar information because solar is the prime factor. So this is from systematic literature survey. Okay. So we got to know these are the concrete data that is required for yield prediction in the context of yield prediction. And whatever is labeled in white are just abstract, which means few researchers have utilized the subset of these data, okay, for yield prediction. Okay, it is all trial and error measures. So researchers will try, okay, let me add in this data set if it is going to accurately predict my yield. So they'll check for it. That is the work of a researcher. Okay, I'll have this data set.
Only the real-time data you do, or you will go
No, this is from
historical data also.
So this is from system literature survey. These are the data set that is important for yield prediction. Okay, I have not mentioned what is the data also. So I can take crop information. They have taken, few researchers have taken growth process, which means the growth they have measured physically. What is the height of the plant? What is the crown size? They would have measured. So what is the parameter they have not mentioned? So few are utilized growth process, leaf area index. So they tell or the size of the leaf, okay, will measure the age of the plant. Okay. The crown, I just take an image of the crown. What is the leaf area index? That indirectly tells me what is the age of the plant. Okay, that is one thing. So there are typical parameters. So there are so many phenotypic parameters, there are environmental parameters people keep adding, and they try to understand, yes, if the yield prediction is appropriate or it is closer to reality or not. So this is the condition. So these are the abstract. What is labeled in white are going to be the abstract. So this systematic literature review has also understood that, okay, it is not only for the parameters. So now people have also tried multiple machine learning algorithms. Okay, data is available. So many data are there. I apply for all machine learning algorithms. It is all trial, right? As a researcher, we do it. We try to apply. So according to a valid data from the research paper, it is mentioned that neural networks have found appropriate by 27 researchers who are published in indexed journal. Okay, they have referred. And people have used linear regression for yield prediction. 14 researchers have indexed or referred publication who have used linear regression for yield prediction. So this is not limited data, this is an authenticated data, that's all. From a repository, they have searched for keywords from a repository. So that is how the systematic literature survey is done. Okay, you give keywords, okay, it will analyze the papers, we have to analyze the papers on certain research questions we will put forth, and there will be an output emerging out of it. And you will understand, okay, how is the survey, just a survey or review. So you have random forest approach being deployed by 12 researchers. So they are just to understand how or which algorithm is used most. Okay, and somebody would have included an extra parameter. Some kind of research would have happened with all these 27. Okay, all will not publish the same work. So there is some delta variation amongst their work also. Okay, so now the most widely used ML algorithm is neural network with respect to yield prediction, and the survey also tells that most widely used deep learning algorithm is CNN. Okay, so for yield prediction purpose. So this is so now under what basis this survey is done is that machine learning algorithm based crop yield prediction papers have been synthesized. 50 ML based papers and 30 deep learning based papers were selected based on the keywords, and this systematic literature survey has been conducted. Okay? Okay. Now is the main picture. Okay? Our ML is coming into role. Okay? So now ensemble models. Okay? So there are variety of machine learning algorithms. So now or generally for yield prediction, people go for ensemble model architecture. So ensemble architecture is that I combine different models, okay? I apply the data set to random forest algorithm. I combine the data set, give it to random forest, it will predict one yield. Again, I give the same data set to gradient boosting, and it will give or it will predict some yield. Same data set. I will give it to another machine learning algorithm, be it neural network, it will give some prediction. Or all the outputs will not vary greatly. Okay, they will just vary in some threshold values. Okay, so there is some variations. So now I just go for a stacking model. Okay, which I take up the inputs of all predictions coming out. Okay, now instead of having one decision being made, now I have multiple. So now this meta learning or stacking process is nothing but it is kind of a shallow network. There is no deep network. It is kind of regression model I applied at this stage. Okay, take all the inputs. Now the inputs will be the prediction values. Okay, and finally I get one final prediction emerging out of the stacking process. So that is called finding the output through ensemble model architecture. You use multiple models. Okay, apply the same inputs, get the varied outputs, which are not greatly varying, but okay, closely varying with each other. And now you give it to another regression model or a shallow network, okay, and find what is the output. That's all. So this is the majorly used model in the agriculture yield prediction technique. So today I will be just discussing about this random forest. Only one method under this condition. So random forest approach. So now, okay. So this will be better if I have a next. Okay. So this random forest approach. So I have some data set. Okay. I bootstrap it. Bootstrap it is create some duplicate data set out of it. Okay. Sometimes I pick the data set, some few data sets. Okay. I bootstrap it without any replacement. I create some duplicates. Fine. So now, this random forest data set is that it is a subset of decision tree. Okay. So decision tree is that I give some question, it will tell yes or no. Fine. So now this random forest has this multiple decision trees. Okay. Under multiple contexts. So now the context of discussion is yield prediction. So if I go ask a farmer, okay, how is the yield now? Okay, just forget about random forest. I'll cut it down simpler terms. You go to a farmer, ask what is the yield. Okay, he will have his own perception towards yield definition. Okay, sometimes he'll say the rain is good, the season is good, the rain is good, so I expect a better yield of 80% yield I will expect. So go to another farmer, you ask what is the yield, what is the predicted yield. Another farmer will have another perspective looking at the soil condition or looking into the healthiness of the crop, he will tell the yield might be 70%. So it is something like this random forest, you are going and asking some 100 farmers what is their yield, what is the output, and everybody will have their own decisions based on their own perspectives, okay, based on their own experience. So very similar is that 100 farmers here are nothing but the 100 decision trees. So each will have different deciding criteria. So they are going to work in coordination. So the same data set is given, it is asked to give some output, and everybody is going to give different decisions on different perspectives. Very similar as this random forest. So it is going to take the features and give some output. Okay, this is take some features randomly and going to give the output. So very similar to when you are asking one question to multiple people and taking the answer, accumulating it and finding what is the final output. So this is the random forest approach. So you take multiple decisions. So your decision is not based on one feature. So it based on multiple features, based on multiple perspective or dimensions, you are able to take that last final decision. Okay. So that is the case with respect to random forest approach. So here random forest and yield prediction come from the ability to capture the non-linear relationship between the growing condition and the crop yield. So now the model creates multiple decision trees. So for yield prediction, it is estimated, or generally it is around 500 to 1000 for yield prediction, which are trained on bootstrap. So bootstrap, I have limited data sets only. I do bootstrapping means I try to create duplicates. Okay. Duplicates with replacement or without replacements, that I do it and have some voluminous data, my data set is increased. Now I have provision to take multiple decisions. Okay. Now the agricultural applications bootstrapping is particularly valuable as it helps in the inherent variability in farming data, including seasonal fluctuations and the extreme weather conditions. So these are the basic things that we do with respect to yield prediction, with respect to random forest approach. So typically in an ensemble model, I apply this approach, I get what is the yield. Okay, there will be multiple decision trees, I will have a final output. Now I fix this output over here. So for this given data set, I will have one output emerging out. Similarly, based on these machine learning algorithms, I will have outputs at different, with different, a slight variability I will have. Then now I have another section which is called as meta learner. So now it is going to have a simple regression model where it is going to take the simple the output data, which is the predictions from various machine learning algorithms, and now it is going to give us the final output for yield. So this is with respect to ensemble method of yield prediction. So next, okay, now we are done with the first case. Now we are going forward with the disease detection and classification. So as I told you, disease detection and classification, primarily we work on crop health or leaf health or everything at a closer proximity. So images are generally used for disease prediction because your disease are generally shown out. Okay, you cannot measure it using physical sensor or field sensor, but it is just physically shown in the, or it is exposed in the leaves condition or the rooting nature. Okay, you can see all the phenotypics of the plant would have changed if it is attacked by a disease. So you go for imaging techniques with respect to disease detection and classification. So here the input sources would be the RGB images, multispectral data, and some thermal sensor data. So these are the basic input sources, and you go for image enhancement, because when you are talking about image, you will have image enhancement because you are capturing the image at open door condition, bound to have different lighting conditions, there will be shadows. So there are a lot of image enhancement you should work on. Okay, image processing has to be done. Because it is just an open field, you are trying to capture a data with a camera at an elevated positions. So you may have, if there is a tree around there, you will have a shadow. Okay, based on the lighting condition, whether it is a midday or early day. So all these matters with respect to the image that you capture. So image enhancement is a part and parcel of this process, pre-processing method. So you will have image segmentation and feature extraction. So basic features you will extract from the image, and you go for the feature extraction. So now the input source is image for disease detection. The next is, what is the, if I told you in the earlier survey, if it is an image, something that is go well with the image is machine learning algorithm is CNN. Okay, so we have, so what I mentioned here, ResNet, VGG16 are pre-trained CNN networks. Okay, so as earlier mentioned, so we are into edge computing. So these pre-trained models will be deployed in edge devices. Okay, so that it captures it captures the image at the ground level, and this edge devices is there to already I have deployed this machine learning algorithm. Your ResNet or VGG, which is a pre-trained network, I will deploy it. Just with some fine tuning, I will be able to exactly able to find disease prediction model into the device itself. So now at the device level itself, I will be able to achieve or predict what is the disease, detect the disease. Okay, just capture it, find it over there, classify what is the disease. I will be able to detect it, I will be able to classify at the device level itself. Okay, I don't take the data outside, sit into the computer, work on it. No, at the node level, I will be able to assess the data. So that is the importance. So we have the model type ResNet and VGG16 working on it. Okay, I suppose the font is very small, I'm sorry for that. So okay, you have data acquisition, so acquisition of the data from various image sources, data sources. So if your imaging frequency I mentioned, so if you are working on an RGB camera, then you can take a daily. Okay, you can continuously monitoring your growth of your plant and understand whether it has attacked with disease or what is the healthiness of your crop, you can have a daily basis analysis also. So you go for, if it is an RGB image camera, then you go for daily RGB images. If it is a multispectral scan, then you go for weekly. And if it is a drone survey, then you go for bi-weekly. So this is the sampling rate for the imaging frequency. So you have the data being acquired. The next thing, as I mentioned, it is the image processing. Part of it is image processing that you have to definitely do. So as part of image processing, you will have enhancement, you have segmentation, you have feature extraction, as I told you, normalization, then augmentation. So these are the image processing that you will take care. Then after which you have, in pipeline, you have deep learning algorithms, so CNN. So in CNN we have different layers or different filter layers across. And at last you will have result analysis. So you will have disease classification, you can have severity assessment. Okay, there is an attack, what is the severity? Okay, at what stage it is. So you can go for early detection or indication levels. Next you have treatment plans and risk assessment. So these are all provisions with the image data source. So people go for risk assessment. There is a cyclone, yes, you take satellite imagery and you go for risk assessment. Somebody was asking, we are not able to access the satellite images. In this case of risk assessment, there is a possibility that out of interest we capture or we retrieve the data from the database and we go for risk assessment. So these are the provisions that we can do with the image data sources. So detection metrics, you can have overall, as I told you, for the metrics would vary for detection levels. You will have accuracy of detection as a metric score. You will have recall, precision, all part of the metric score with respect to images that you're working on. Next is performance by condition. So since it is open field images, you are bound to go with the next level, which is performance of the model with respect to condition. So whether clear weather or cloudy condition, you're taking or accessing the data in the morning or noon or in the late evening. So that all depends. So how well your machine learning algorithm is working for all these conditions. So that is performance by condition. Okay. So that also we can analyze our model. So this is assessment with respect to the machine learning algorithm. In this context, it is CNN, how CNN network or architecture is working across these conditions. Whether it is a clear weather, it is working, yes, your algorithm is working. Whether it is, if you take a data in the early morning or in the midday, it is working well. So all these are performance-based metrics. Okay, just an overall picture. So it is computer vision. So when I talk about image, the context I talk is vision. Okay. So now I have computer vision based technique for plant disease detection. So I scan it. Okay, I scan across for images. There is a digital scanning. So I acquire the images. Then I go for in case of detection, I analyze the nature of the leaf. Okay, because it is profoundly, your disease is predicted from the condition of the leaf. So I go for image extraction of the leaf only. Okay, because if I capture, I cannot capture the leaf only. I will capture the area around the crown of the crop. I will capture. Now I have to segregate an image which is leaf. Okay, which is of interest. So I'll take which is of interest. I will take that region. Then I go for pre-processing. Now again I split the data set as training and testing for validation, all that I do. And then I just give that training and the validation data sets to the CNN architecture. As I told you, the CNN architecture or deep learning model is represented by this because it is layer of filters. Okay, it is layer of filters. So it has to cross across the filter. Okay, say for instance, these are the few healthy and some infected crops images that are being captured at I just mentioned here. So this is from a potato plant and this is from a maize leaf. Okay, so this is just an indication of where it is attacked or a disease is detected. So people who are into biology, they'll know if this is an indication, then what is the related disease. So they'll be able to appreciate it from the image. So this is how the sequence flow is there. Now the big picture is CNN architecture. So now we'll work on CNN architecture for pest detection. Pest is that some pest has been attacking the leaf or not. So that has been the case that we are discussing now. So say for instance I have an image at the input layer. Okay, now I have an image at the input level. Okay, the next, so this is the architecture. If you see, it has got the second layer or the first filter that is across is your convolution layer. Next you have pooling layer, then you have fully connected layer, then you have the output layer. So this is the architecture of the CNN. So now your input layer is going to handle the RGB image, which is represented in the pixel values. Okay, so it is into 3, so it is RGB values. So this architecture I'll be able to better explain you. Okay, so here it is mentioned. Okay, so the application of each layer, your first layer, which is your convolution layer, is used for feature extraction. Okay, you extract the features. So okay, a leaf is there. You are trying to identify what is not appropriate a leaf feature. Okay, you identify some wings in it or some legs in it. Then you go for dimensionality reduction. When you go for dimensionality reduction, you are trying to zoom in the picture of a leaf. Okay, then you have to be able to identify there is an insect over there or a pest over there. So that you will be able to identify the second filter, which is your pooling layer. Next you will have the classification. You identify if that is a pest or not. Okay, you classify it. Okay, then you have what is the probability of pest class. If this is a pest class, then what is the variability, whether it is belonging to this category or the other. So that we will be able to identify from the image. So this is better explained in this slide. So first is the input stage. So at the input stage, you have image feeding a photo of a crop into a digital scanner. So you have a digital scanner which takes the photography of an image of a plant or a crop at a higher elevated position. So now whatever you get at the input layer, what you get at the input layer is a 224 cross 224, which is a pixel size with 3 colors. Your RGB image you get. Now you will do the basic pre-processing at the input layer, which means you will go for some color correction, brightness, contrast adjustment. All that process you will do at the initial state of at the initial input state, and you will go something like as you have done for the earlier thing, you will do image normalization also. So next, after the input stage, you will have feature learning stage, the second layer. So your second layer is your convolution layer. So if you are seen here, so there are 3 convolution layers all in picture. So we will understand the each layer. So the first layer is the basic feature. So it's like a student learning to draw. The first it looks like basic shapes. Okay. First, if you ask your kid to draw, he will draw something. Okay, you will understand. Okay, this is an apple. Okay, if I draw a circle, it is an apple. Or it may be an orange also. But some basic structure you will be able to identify in the first filter. So that is your convolution layer 1. So next layer is understand the pattern. Yes, it is whether you just take an image. You find, say for instance, you are taking a picture of an animal. Okay, it is small. Okay, it is measurable height. So it can be a dog, a small pug dog, or a cat. You just identify it. And now you go for the next pattern. Okay, it has got 4 legs. I'm able to identify. So that you will understand when you zoom it. Okay, it has got some 4 legs, 1 tail. It has got, yes. So next, you are trying to zoom in the image. So that happens in the second layer of convolution. So you will now understand the basic features. Yes, 4 legs and 1 tail is there, 2 ears are going to be there. So now you are understanding the features out of that image. If it is a small animal that you have captured in an image. So next, third layer is complex feature. Yes, now you will understand whether it is exactly a cat or a dog. Yes, because you are completely zoomed in. Okay, and now you will be able to identify all the features. Yes, its mouth size and its face structure and all that, you will be able to identify what animal exactly it is. So that is the filter level that it has to undergo. So as human visionary system is acting. It tries to understand what is the basic image, yes, what are the dimensions, then features out of it. So that you do it in the convolution layer. So next is pooling. You are trying to simplify it, okay? Simplifying the image, okay? What is my interest now? That I take and I zoom it, okay? So that is, okay, now I in an application of disease detection, now I have identified it is a pest. Now that region I will start exploring or finding it, it will go to the next filter. So now each convoluted layer image gets simplified, and zooming into the photo you see the big picture of it. So now we are now interested with the pest. What is the pest that has attacked my leaf or not? So now that region I will try to zoom in out and check. Okay, is now I have identified it as a pest. Now what kind of pest? That is your disease detection. What kind of pest has attacked my leaf? So that we are interested. So that will be identified in the next layer, which is your pooling layer. Next, in the classification stage, I will be able to identify or classify what type of pest it is that has attacked my leaf or crop. So that I will be able to get the details at the next layer, which is your classification stage or dense layer, I call it to be, which is your fully connected layer. So you should need multiple inputs. It is a network structure in CNN layer, which is called to be the dense layer, which is going to classify which kind of pest. At the last, you will be able to find a final answer. Yes, this is a pest and this is of this category. So this I will be able to tell. So this is how from an image I will be able to detect whether it is a pest, what is the classification of pest that has attacked my crop or plant. So this is the thing. So this is the application of CNN. So CNN not only in agricultural imaging, it is widely used if you are a researcher. CNN is widely used for images, the machine learning algorithm which is used for images. So with this, I'm just having a close on this disease detection. Quickly maybe ML for resource optimization. So with respect to resource optimization, we have three heads involved. One is irrigation management, fertilizer optimization, and energy management. These are the major things I will, of course you will have land asset management, everything is there. So what primarily that we see is all these three heads under which optimization can be greatly enhancing your farming practice. So across irrigation management we use reinforcement learning, so which I will be discussing as part of this case study. So reinforcement learning, you have time series prediction and decision trees involved for irrigation management. For this we have used system sensor level integration. When it comes to be management, you will have actuators or control algorithms in picture, so you have control systems with feedback loops. So that is mentioned over here. In fertilizer optimization, so prediction models, understanding about the crop stage and what is the appropriate nutrients level required at that stage of growth of plant. Okay, for that crop maturity level, what is the appropriate nutritional needs has to be identified. So that is your nutritional needs. And application timing. So when I talk about optimization or resource optimization, I cannot apply fertilizer at randomly. So when there is a deficit in nutrients, then I will apply fertilizer. Okay, that is where it is going to greatly appreciated in precision agriculture. So you are trying to precisely or optimally use the resources. So here the resource is fertilizer. So I will be able to inject the nutrients or apply fertilizers precisely. Okay, so I will be able to application timing is important. So next, prediction models to find rate optimization. At what rate I should apply the fertilizer. Okay, randomly, if it is at initial stage of growth, at what I will have a different rate of application, amount of application also would vary. So if it is a grown to a certain level, then the application of fertilizer levels would vary. So what is the rate at which I apply? So that is called to be the rate optimization. So with respect to agricultural 3.2, variable rate technology, which is facilitated by GPS, is one of the important technology. So we have implementation of variable rate. So at various rate varied rate of fertilizer being applied. So now, okay, implementation for precision application and cost of. So when you are trying to precisely use your resources, ultimately you are working on cost optimization. Next is energy management. So this is another agenda when it comes to resource optimization. Okay. So without, I think I quickly make it up. So digital farming solutions. So with respect to digital farming solutions for smart irrigation system. So I have various of data that is collected from various sensors, okay, when it comes to irrigation. The first case, I've taken up the first case as the case study, irrigation management. So I take, okay, to understand the crop nature, the crop spread or drought, I capture a drone-based image, okay, to understand the crop variability. Next, I will go for the field sensors. So I will deploy field sensors and some weather data from weather stations, some environment monitoring sensors data will be available, as well as, so since it is irrigation monitoring, so I will be able to understand the soil nature. So I will have the field sensors related to the soil moisture content will be available, and some satellite imagery for understanding the what is the crop level, okay, maturity levels. So from this all, the data collections will be there. So there will be an, because we are trying to, it is smart irrigation, so I will sit remotely, okay, and I work on irrigation patterns. So for that reason, a gateway, which is you're sending a data through cloud is being mentioned over here. So then you have a cloud server. Next you have an IoT edge device. So this edge device itself is going to take up the decision whether it has to operate the pump for irrigation or not at the edge level itself. So it is the edge level. So it is going to decide, so what this edge device is going to take up the decision. So it is going to take up the decision on timing, what is the volume of water that is to pump, okay, what is the pump speed. So all these levels of decisions can be worked with respect to edge devices. So if you see, end result is application in the field. So you have one pivot rail of water which is sprinkling all over the field in order to manage the heat stress. When it is very high temperature prevailing, they go for heat stress management. They simply spray water across. So that pattern, where it has to spray, when it has to be sprayed, so that has been automated. Next you have sprinkling irrigation, which you would have seen in multiple farms. It is available, drip irrigation, all available technology or implemented technologies only. So with respect to sampling data of the different types of sensors that I deploy. So soil moisture sensors, I collect the data every 15 minutes. Weather data sensor every 5 minutes. Flow rate, flow rate or the pump rate, pump water flow rate, continuously I keep monitoring it, and pressure is in real time. So this is the basic data set and how it has been deployed for smart irrigation. So quickly, under this category, we have seen the first reinforcement learning. So I just quickly touch upon reinforcement learning. So reinforcement learning is that, okay, in simple terms, I have a dog, okay, I train the dog, okay. What I do, if you catch this ball, I'll give it a reward, I'll give it a treat. I'll offer a dog food, okay. So if I how do I train a dog? I have a dog, I have to train a dog. What do? So I give some activity. If it does the activity, then I will give some award to it, which means I give some food, or I offer some food to the dog. So this is how in training of a dog happens. So it is your response of training will be understood from the environment. So that is the case. So you award it or you penalize the dog, okay, based on the situation or based on its response to the situation. Okay. So now you understand same way. There is an ML algorithm. Okay. If it understands the situation, then it will be rewarded or else it will be penalized. As simple. So based on this awarding and penalizing, we expect that the model will learn over a period. Fine? This is the case. So now here every action has an effect on the environment, and the environment then gives a learning algorithm feedback. Okay, this is the case. And how does the learning process happens? So the irrigation system works in the same way. It makes sessions about watering. Okay, it first waters the field, sees the result. Okay, oh, I have done excess watering. Then for the next time it will not do. Okay, the decision would change. So over the experience, it itself penalizes, awards it. So okay, this measure is called to be the reinforcement method of learning. Okay, you give it. Okay, if there is a data set, there is an environment. You add to the environment changes. There is a reward or an for the every action. So there is a reward or penalizing action for every action that takes place. Okay. So by this way, we expect that like a dog gets trained to the situation, we expect our models also to get trained. Okay, over the situation or the environment. So now under what grounds it is going to learn? How the decisions are made by the ML algorithm. So how dry is my soil? It will analyze first. How dry is my soil? What is the weather forecast? So how healthy my plants look? So how much water should I water yesterday? It was enough or not? All the data. So all these questions will be answered as data sets that you give. So you will give a data set, okay, and from that it is going to learn, or from the actions that it has done, it is going to learn. So this method is very appropriate for smart irrigation management. So the reward is like the plants are going to be healthy, it will save water, and using too much water, it's something like the plants let it to dry. So this is the penalizing action that you not seen. So based on the award and the penalizing nature, you will be able to understand the system or the environment and act appropriately. So your machine learning algorithm will act appropriately to the environment conditions. So for that, to answer all these questions, you should provide the algorithm with appropriate data. You should understand what is the soil nature conditions you have to give, and all that you should be able to give it up as a part of data, so that it is going to learn the environment and it is going to act appropriately. So this is with respect to smart irrigation system, smart water management in the irrigation. This is with respect to the presentation. Quickly, next 10 minutes if I have, I'll just. Okay. Sorry. For now, any doubts?
Madam, why don't you take this crop water requirement?
So you can take. Because here if you see how much water was used yesterday. So you should give the history of watering data. What was required yesterday? So what was the weather condition yesterday? So it will learn. So a part of this data, as you told, what is utilized, water utilized yesterday, which is the history of data. So to answer this question, how much water was used yesterday? Which means I am already giving a data. What is water level yesterday? So whether it was enough for the plant, I will be able to understand and mentioning its soil condition. So it is appropriately it's going to act, your algorithm. So any other doubts closer to this context? Okay, I suppose I touched 3 machine learning models. One is random forest, CNN architecture, and now reinforcement learning. So these are, there are a lot of pool of machine learning algorithms. All things is little, it will be exhaustive, list is exhaustive to cover in a day. So 3 for today, yes. Maybe you have the lecture for another 4 more days are there. You may expect other techniques to be discussed. So as of now that we have covered today, any doubts with respect to advanced machine learning algorithms for advanced farming techniques? Okay. So if no doubts, I quickly go to the journal discussion. So today's part of journal discussion, I will be discussing on the work on modeling greenhouse environment using optimally designed bootstrapping artificial neural network, which was published in Neural Computing and Applications in the year 2019 in an SCI indexed, Science Citation Indexed journal. Okay. So first, before that, I have a slide, but I'll quickly tell. So what is greenhouse environment? So anybody is aware? Maybe 4 sessions were over. Anybody has discussed about greenhouse technology? Okay, so everybody is aware of open field cultivation. Okay, when you
The plant is cultivated in the green.
yes sir. That's what anybody has understood. There's so people are from various backgrounds. They'll not be used to the terms. So maybe I'll let you know. So things is that everybody is aware of open field cultivation. So if you are cultivating in a closed environment, in a controlled environment, where you are able to monitor and control the weather parameters. So that type of technology is called to be the greenhouse technology of farming. Okay. So this work is appropriately oriented towards greenhouse farming. The first part of the paper discuss about modeling the greenhouse agro ecosystem. So agro ecosystem because it is collective of multi-parameters. Okay, because there is an interaction between a plant and the environment in a closed condition. There's a closed interaction. Okay, so you call it to be an agro ecosystem. So you have modeling of the greenhouse ecosystem using optimally designed bootstrapping AML. So this is the major part. So you are trying to model it. Okay. So I'm just skipping. These are the introduction slides. To just tell you what is a greenhouse, but due to the time constraint, just quickly going to the. Okay. So somebody was. This is how appropriately a systematic literature survey would look. I give a keyword, and I analyze multiple papers, so I put some research question, and what emerges out is this connected graph. So if you see, so for environment control of plants, you can see soft computing for greenhouse climate control is the emerging, which is coined around so many keywords, appropriate keywords. So it will analyze multiple research papers which are oriented towards environment control of plants, and what are the related keywords we will be able to get. Okay, so you will have a big picture of what are at least the keywords around this research topic. Fine. Okay, this I was working. This is my work actually. So this has been done in collaboration with ICAR NRCB, National Research Center for Banana. So here, this is what you see here is a greenhouse. So banana in the sense, here they harden. Okay. So for certain weeks, right from the sampling stage, to a certain stage they grow or keep them in a controlled environment. So which is called to be the greenhouse. After which the samplings will be moved to the field. It is a month or so. It will be hardened in the controlled environment. It's something like a newborn baby, put it in an incubator. Just to give it all warm condition, not exposed to the open conditions. So the samples which are from laboratory to, instead of moving directly into the field, it will be moved into the intermediate stage greenhouse. So this data which I collected, or which the work was done, was the data set available from this greenhouse only. So these are the stages. So it starts from here. They have all these are methodologies or plantlet generation from embryogenic levels. So this they do it in an RCB. So this is the case, they'll put it in the, so these are the cases where it is hardened in the greenhouse. So the first stage and the second stage hardening. So we are plants will be hardened. Just you put it in an incubator, coming out from the embryological lab, everything will be hardened first in the greenhouse, controlled environment. So this is the case. So what we were modeling is that in that case, everything has to be controlled because they are very small samplings or plantlets. So this is the greater representation of the agro ecosystems. You see, you have the greenhouse model, which is the environmental model, so which is affected by weather variables, control variables, and state variables. More technically talking, and there is an interaction that is between the greenhouse or the environment itself and the crop, because the crop, it is a greater interaction between the crop and the environment. So this is a larger picture. I was able to understand or estimate the growth rate also. for the period that was hardened in the greenhouse. Okay, the basic data which was collected for that research work was from NRCB. So the basic data sets are given. So this my work is to understand the ANN model, optimally design my ANN model. So ANN is artificial neural networks. So I have multiple inputs, set of inputs, and my objective is to understand what is the environment condition. So optimally designing is only the first area of work that I have taken. So first, before that, we do first physical modeling. So based on the first principle model, based on the thermodynamics, we have the defined. We can define the temperature inside the greenhouse environment. So that was first for validation of our model. We just worked on this physical modeling. So after which, so the basic work is identification of ANN model for greenhouse. So that was done. So here we have one input layer, one hidden layer, and one output layer our model had. So we had 14 neurons with hyperbolic tangent. If you are understood ANN networks, so you will have input layer, hidden layer, and output layer, and the number of nodes in the hidden layer is 14. So we had worked for 2 months where it was hardened in the greenhouse, where the samplings were hardened in the greenhouse. So that is the data set that we have collected. So many days of data set we have for various parameters. So this is how the completely connected. So all these are the data sets that we have collected. So you have humidity, Julian day, ventilation rate, temperature, solar, what is the wind, everything. Everything is environmental parameters we have collected. So which is with 14 hidden neural network, hidden nodes in the hidden neuron, hidden layer, and you have one output node in the output layer. So this is the basic model that we have achieved with a completely connected network. So what is blue representation is a physical model that we have applied, and how our completely connected neural network is just following up the physical model, and what is the error index has been given up. So the actual work is on optimal design. So if you see the computation level that involves in understanding the output is very complex because it is fully connected. So the ultimate agenda was to optimize this network. So that your computational efficiency is cut down. So that is the major agenda. So we have used OBS algorithm, which is pruning algorithm. So there is, if you please could refer, you can just refer how the algorithm works all. So there is an algorithm which is optimal brain surgeon. It would cut out the neurons or nodes for that matter and check if the output has greatly changed. Okay, so we'll do this for each node, okay, and find, you train the algorithm for the cut node and you will achieve whether it has doing well if it is cut also. So in this way we will try to understand which is significant input or significant node for this architecture. So that will be understanding. So this is an predicted output with 76 weights, okay. So which is pruned to an extent. It is not optimally pruned, it is pruned to an extent. You can see that the neural network predictions has little shown its deviation from the physical model. So the error index is plotted against. So now this is the optimally pruned. So sometimes if you are pruning the right node, then it's fine. It will not optimally, it will not deviate much. But if you are pruning out a significant node, okay, for the purpose of pruning, you prune everything. Then if you are cutting down an important neuron or node, then ultimately you will not achieve your output at any cost. So you have to optimally prune. So we have understood that you can go for an extension of this level of pruning. Okay. If you see, we have identified out of this pruning what is insignificant input which is not required at all. You need not measure. Okay. Instead of measuring all these, what is the heat accumulated, all that you need not measure at all because you have indirect connections or data which are reporting to this output indirectly. So you will be able to identify what is significant input, what is insignificant, and you will be able to also reduce the architecture greatly, wherein your computational efficiency would be increased. So this is the work that initially was done. We had used OVS optimal brain surgeon method. So this we have tested across. So this is the correlation that we have achieved. So all closer. So if you see it lies within the confidence band. So this is the optimally tuned with 15 weights. It has performed well within the confidence interval. So if my predictions were lying outside, if it is an outlier, then the confidence levels are not met. Okay, so it is all well within the confidence levels. So okay, this is the inference. So you can have not always a bigger dimension of the neural network to perform well. You can have an optimal network to perform well also. So that they call it to be the dimensionality of the network is really mattering. Okay, so as a part in the same research work, we have growth, because we have crop model also as a part of agro ecosystem. So modeling of the crop growth was also done with ANN. So this is what it looked like inside the greenhouse. The samplings will be placed for 2 months for it to harden. So those data sets. So here you will have phenotypic to measure the crop growth. You will have phenotypic parameters also, which means the height of the plant, the crown size, the leaves index size, everything will be noted. So physical measurements only for height. We'll take the sample, might measure, because everything is from fresh from a laboratory. One set is from a laboratory, has moved to the greenhouse. So if it is okay that you randomly measure for few samples, what is the height, to understand the growth nature, whether it is what is the growth stage, we can be able to answer. So you have the environmental parameters and the phenotyping parameters, which means the parameters which is related to the growth. So as I told, we have gone for, since the sampling size is less, we have gone for bootstrapping technologies. So you duplicate the samples and you create models out of it, and you go for ensemble neural network, and you identify what is the crop growth rate. Okay, so this is the periodic measurements that we do, and these are the periodic measurements that we take up. What week it is belonging to, okay, what is the height, what is the width, number of leaves that has come out. So all these are physical measurements that we do. And this is about bootstrapping. Please get back. You will be able to understand what is bootstrapping in a better way. And ultimately we have used the estimates were within the confidence interval. So this is the estimated growth. Okay, gets saturated like that. So days of the week. We'll be able to, so your crop growth rate is understood from getting the net assimilation rate. So this one parameter we apply in this formula. So we will understand what is the crop growth rate indirectly by getting the what is the assimilation rate of the plant. So that is, so this is the summary of the statistical industry. What is the RMSE and the best performance index? So I'm done with the presentations. So this is the research work that we carried in the initial part. It took a year to publish. That is the initial work that we have carried out. Any doubts?
In confidence interval, so what percentage you have chosen?
So we go with 90% of confidence intervals, because from the, what is the data, you cannot deviate more than 10% analysis.
Have you statistically tested in the statistical?
Yes, statistically tested. It is the intervals is given by the NRCB. So we don't have the biological terms. So they give us the values. This is the confidence levels. If you deviate beyond, so we are not expert in the domain. So they are the that is how the collaboration works. They tell us this, and we'll be able to give the engineering solution.
The confidence interval. Normally we have to use for the 90 or 95, 99% confidence interval.
For this we cannot, because it's all physical measurements that we do. Our measurements may be wrong, little varying, so that is the case.
And also you are choosing some parameters, right? For in greenhouse.
Yes.
In the table, in the ANN model.
Yes.
So what are the controllable factors and what are the
So if you look uncontrollable, the things that we can control in the greenhouse environment is the temperature and humidity, because we have ventilation rate to be adjusted.
what about the fog?
Oh, that's what. The humidity, fog in a sense, humidity is what we try to control. So what is the humidity? Because we at different duty cycles we sprinkle the fog you call. So at what rate you spray is what is the control measures that we can take with respect to the optimization. So apart from it, we don't have the actuator to work on in the facility that we have listed. We have facilities which work on air conditioners. Now you can set 16 degrees also, it's possible. So there they don't use air conditioning, which is not a greenhouse good option. So we use.
It's also very difficult to maintain the fog in the exactly.
No sir, we have sprinkler moving across the greenhouse.
Entire
greenhouse. So it is fully automated actually. So there, by that case, you will be able to control at all levels. So only the exhaust fans only is responsible for the ventilation that is prevailing in the greenhouse.
General question.
Yes sir.
You are branch to electrical engineer.
Yes sir.
How you?
No, I am basically from control background. So greenhouse control was the objective that was proposed to me when I was a researcher. But I have worked beyond also, so that I am able to secure a job in electrical domain. Though I have taken up greenhouse technology as a research problem. Now I work on Industry 4.0. So somehow I'm connecting smart.
Now
5.0 also, just tell you, in the automation, in any terms, not only in agriculture, any ways we'll be able to appreciate it. So
now
that
we
is
can move on to smart agriculture.
Yes, sir. That is the era going on.
Thank you.
Thank you, sir. Yes, please.
Are there any machine learning model which can analyze the feature changes or pattern changes in the leaf when it is getting affected by a disease?
That's what I just discussed. When you are talking about the disease, the major thing is the capturing of the data. So if you are able to capture the data, work on CNN model, what I have discussed now is that I have shown the healthy leaves of a potato and maize plant. So it was able to perform, CNN was performing well in identification of the class of disease that has been attacked. So it is possible that we have discussed today also.
That is
From the
other identification, right?
No, it is disease detection only.
Even pattern changes in the disease can also be identified.
No, if you are able to give all the inputs, if this is the, you have to give the algorithm the knowledge.
Okay.
So you should have an expert who is defining or who is an expert in identifying the diseases. So we will be able to extract the features, tell you this is the pattern. Now it is for you to give it the intelligence that or classify or tell the class, specify the label the classes. Any other doubts?
Any other doubts? Okay. On behalf of Electronics and Instrumentation Engineering at Annamala University, I thank Dr. Revathi ma'am for his enlightening lecture of applications of machine learning in smart agriculture. I request Jaya ma'am to honor the Revathi ma'am with the shawl and memento.
Pleasure.
He is also working in the machine learning application to process control.
Thank you, sir.
Thank you.